Welcome, Warhawks, to another edition of Seminole High School Geometry. This is Mr. Tipton. Today we're doing Chapter 1-7. It's going to be some fun stuff. We're talking about concurrency of different line segments as they relate to triangles. The first word we're going to have to know what it means is the word concurrent. Concurrent means where lines come together. In this case, we're going to be talking about three or more lines, and in this case, actually, it's really going to be three lines when we're talking about these triangles, but it just means they come together. So here we see three lines. We would say that they're concurrent there at point A. Let's go to the next slide here. The first word we get to is called the circumcenter. It's the point of concurrency of the three perpendicular bisectors of a triangle. We see something here. This is a special triangle here. You may already be able to guess what kind of triangle it is, but it's actually an equilateral triangle. Equilateral triangles have the exact same length sides. So when we're doing perpendicular bisectors here, what we do is we take and we drop a line that goes from a vertex to the opposite side. Actually, it doesn't have to start at the vertex, but it goes to the opposite side at a perpendicular angle. So meaning that 90-degree angles are created here, 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 the bottom. Sorry, those aren't the best boxes. There and there as well. And we can see that they are concurrent here at this middle point. This is another type of triangle that you may see. It is actually a right triangle. So here it is a right triangle. And notice something special about this is that no matter what, when you have a right triangle, the circumcenter is always going to be in the middle of the hypotenuse here. So we can see we drop a line that goes perpendicular from this side to the hypotenuse. There's a perpendicular angle there, 90-degree angle. And then we have one that goes from this side over here. There's our 90-degree angle. And then we have one from here to this side at a 90-degree angle. Now this isn't 90, but it came from this side, and it is 90 degrees over here. But the important thing to remember is that when it's a right triangle, we'll write this, go ahead, show you this. In right triangles, let's make this a little bit smaller. In right triangles, the circumcenter is on the hypotenuse, which is the longest side of a right triangle. It's actually in the middle of the hypotenuse there. And then we have over here, we have an obtuse triangle. It has an angle that's greater than 90 degrees. If you have an obtuse triangle, then the circumcenter is always going to be outside of that. So here's our 90-degree angle here. Here's a 90-degree angle here and here. Those are perpendicular. And over here we have our 90-degree angles. But notice how they don't touch each other inside the triangle. We have to actually extend those, and they're going to intersect each other or come together outside of the triangle. So if you have an obtuse triangle, they're going to come together outside of the triangle. The next word we get to is called the incenter. It is where the point of concurrency of the angle bisectors. So you'll notice something here. This first one, again, is an equilateral triangle, and we see that that is the angle bisector. I dropped it down. It bisected that angle. Here I have an angle bisector, so those are going to be equal to each other. And here I drew another angle bisector. You'll notice that they actually come together at that center point in an equilateral triangle. So let's look. There was our circumcenter there. There's our incenter there. So they're going to come together actually in the same place. It's just an interesting thing that happens because these are actually going to be perpendicular angles. So in an equilateral triangle, the incenter and circumcenter are the same. Here's another one. Here I bisected this angle. This is just a right triangle. Notice how, again, when I draw those angle bisectors, the point of concurrency is right here. It is, again, inside the triangle. And even on an obtuse triangle, when I draw in those angle bisectors, the point of concurrency or the incenter is going to be inside. So it's one that is always inside of the triangles. The next one we get to is called actually the centroid is going to be the point of concurrency here. And these are made by medians. A median is a line segment that connects the vertex, which means where the angles are made, part of what makes a triangle, and extends through the midpoint of the other side. So that point there would be our midpoint. I can show that by marking that. Again, this is an equilateral triangle. Here we have another midpoint. I'll put congruency marks to show that's the midpoint. And here we have another one. Now those are actually all going to be the same. And again, notice how the centroid is right there in the middle of an equilateral triangle. It's going to be actually the same place as the angle bisectors and the circumcenter, or the incenter, circumcenter, and centroid are going to be located in the same place for an equilateral triangle. Here again, I drew a line from the vertex to the other side's midpoint. Oops, let's edit, undo that. I don't know what happened there. And then I drew it from this vertex to the midpoint over there. This is a right triangle. So there, I marked that to show that that is the midpoint. And then from the other vertex over here, so I put 3 lines here, congruency marks to show that that point there is the midpoint. So I connected this vertex over there. They come together inside of the triangle, but we just connect from the vertex to the other side's midpoint. Now, if you had a ruler, you could measure this out and really make sure that those are in the middle, but they come together in the center. Here's an obtuse triangle. I connected this vertex to that side's midpoint, this vertex to that side's midpoint, and then this vertex over here to that side's midpoint. So those would be congruent. Those are congruent. And then again, it comes together in the inside of the triangle. Lastly, we get to the orthocenter, which is the point of concurrency of 3 altitudes of a triangle. Now, an altitude is a line segment that starts at a vertex, so a top or like an angle of the actual triangle, and is perpendicular to the opposite side. So let's look at the different cases that we have here. Here's the equilateral triangle. Again, we start at the vertex and we go perpendicularly, and really it's going to be in the exact same place as all the other ones. So those equilateral triangles are special. The incenter, orthocenter, circumcenter, and the centroid are going to be located in the same place. Here we look at a right triangle. This is the right angle here that makes this a right triangle. So I drew a line that was perpendicular to the opposite side. So there's our perpendicular angle. Then notice how when I come from this vertex and draw one to the opposite side, it actually is the side of that triangle. So it comes all the way down here and makes perpendicular. And then when I go from this vertex to the opposite side again, it is just the side of that triangle. So a special case here to note that a orthocenter is always going to be right there where that right angle of the right triangle is located. So right there is going to be our orthocenter. And then we get to an example of an obtuse triangle. Inside here is our obtuse triangle. And when I draw a line that's perpendicular to the opposite side, it's here. There's our perpendicular angle. It goes from the vertex. But then when I draw one that's perpendicular from this vertex to the other side, it actually doesn't even go to that side. It's going to be outside of the triangle. It's going to come down here. So you would see the perpendicular would be right there to this opposite side. But I'm going to keep extending that all the way down here. And then when I draw this from this vertex perpendicular to this side, you come down here, see there's where they would actually be perpendicular, would be right about there. But I got to keep extending this to create that orthocenter. And so if you have an obtuse triangle, the orthocenter is actually going to be outside of the triangle.
30, the Republican-controlled House of Representatives, in an effort to alleviate the effects of the, anyone? The Great Depression, passed the, anyone? Tariff bill, the Hawley-Smoot Tariff Act, which anyone raised or lowered, raised tariffs in an effort to collect more revenue for the federal government. Did it work? Anyone know the effects? It did not work, and the United States sank deeper into the Great Depression.
Now I know that you guys probably feel a lot like those students right now in that video, but I just wanted to throw that in there. That's a famous video from the movie Ferris Bueller's Day Off, a famous scene there. Anybody who can tell me who that actor is that's playing the teacher in there tomorrow, if you come to me, your first person to tell me in each class, I will give you some extra credit if you can tell me who that actor is. Hope you guys have a wonderful night. Hope you learned something here. Review this, and we'll see you tomorrow in class.